Okay, so let's continue lecture. So now we understand the mechanism and also the structure change after the thermal expansion of the fin. So aluminum fin expand more, silicon fin expand not that much. So at the end, they compromise to each other. You can find the final position of they are. And also during this kind of contraction and expansion, also contraction, you can find out the stress on each fin will look like this. Aluminum fin originally want to expand more. However, the silicon fin won't want to expand that much. So there will be a contraction force, compression force on the aluminum fin to contract it back a little bit in order to have the same length with the silicon. And on the silicon substrate, at the boundary between the aluminum and the silicon need to expand more to have a same extension length as the aluminum fin. Aluminum fin originally expand more than contract back. The silicon being will extend not that much, but will be pushed to extend a little bit more to have the same length with aluminum fin. So at the edge of the silicon, it will encounter extension, the tensile stress, the tensile force over here. So on aluminum fin will feel is a contraction force. On the boundary, the silicon fin will feel the tensile force to push it out. Okay, so the neutral surface won't feel any kind of stress, and also no strain as well. And on the other side, the silicon will feel is a contract, it's compressed. Yeah, because on the top, the silicon have the extension on the top, and the whole silicon will bend, become an arch. So the bottom one will be contract. Okay, so as the position far away from the neutral surface, you will feel more contraction force. Okay, on the bottom. Okay, now we have two questions. After this kind of expansion, what kind of final curve of the structure it will be? That means the radius of curvature. What's the radius of curvature? So what kind of curvature it will be? The second question will become what kind of a bending moment will be generated in this condition. Once you got the bending moment divided by the length, you got a force. The final equation the final parameter we want to get is the force. What kind of force we can generate from this kind of actuator if you have this kind of expansion? Okay, so now to solve this equation, now we have to consider first from the geometry. From the geometry, consider the silicon deformation at the boundary will be equal to the aluminum fin deformation at the boundary because they stick to each other, so they share the same length. However, when you consider silicon case, originally its length is L, but after heated up, so the heating part of the extension will be L times its thermal expansion coefficient times the temperature deviation. Okay, this is from the thermal expansion. However, the thermal expansion itself is not long enough for the silicon to deform because the aluminum fin extends more. So try to draw the silicon on the body a little more further. Okay, so the further thing will be called the delta L. The delta L is caused by the aluminum fin. Aluminum fin will draw this silicon substrate a little bit further from the original place. Okay, so it's called delta L. On the other side, for the aluminum fin deformation, original size is L, the length is L. And after thermal expansion, L times alpha F, the aluminum fin, times delta T. So it's a total deformation of aluminum fin. This aluminum fin thermal expansion is too much actually, because we have some silicon substrate on the bottom to constrain the fin. The fin cannot go too much further. So the fin will be compressed back a little bit from the extension. So the contract back part will be L times epsilon F. L means the original length of the fin. Epsilon F will be the strain encountered. We think it's a uniform strain on the edge, epsilon F. Okay, in this equation of several several things you don't know the the epsilon f, actually you don't know what the epsilon f is. Okay, so we'll try to represent this into different other parameters. So from the geometry, this is a extension of a silicon. Then the other side is extension, contraction of the aluminum film. So they are equal to each other at the boundary. So now we want to replace the parameter delta L. Currently we have two parameters we don't understand the real value. One is delta L, the other one is epsilon f. Okay, so we want to represent length then into the parameters we understand in the formula. So we can do the calculation later on. So first we look into the delta L. The delta L, from the figure here, the delta L means the length here. The length divided by the thickness of the substrate. The ratio will be equal to the ratio of the length over the resistivity, the radius of curvature. So these two triangles, the small triangle, the large triangle, they share the same shape, similar shape. Okay, so the length here divided by the thickness will be the length here divided by the thickness here as well. So this gives you the representative of the delta L to the curvature of this structure. So we put the formula here, delta L over Ts over 2. That's the thickness, half of the thickness of the substrate, equal to the length of the beam over the curvature. Okay, radius of curvature. So here we can replace the delta L, okay, equal to this this parameter, and especially we have a parameter rho over here, but we still don't know how much is the rho. So we need to do calculation later on. But we change the parameter from the unknown parameter delta L into rho, okay, for the equation here. The second one we don't understand what it is the epsilon f, okay. So epsilon f, we want to change it to become the sigma f, okay. And the sigma f, so the sigma f, later on we will integrate the sigma f become the bending moment, m, okay. So now we replace delta L become the function of rho, replace epsilon f in terms of function of a sigma f. So now we have a new equation over here. So here we still have two unknown. Okay, originally we have a delta L, epsilon f. After this kind of replacement, now we have a rho and a sigma f. These two unknown. Other things are unknown parameter. These two are still unknown. So for two unknown parameters, we need to have two other equation to solve it. At least one other equation to solve it. Okay. So the other equation is coming from the moment balance. The moment balance, we will look into the figure. So on the fin, so corresponding to the neutral surface, on the fin, there will be a contraction force over here. So the contraction force will give a moment along this direction and corresponding to the neutral surface. So the total moment generated by this kind of stress will be F times the arm. The arm is Ts over 2. Okay. So this gives you the bending moment of MF. This MF will be balanced by the other bending moment from the second substrate. Okay. From the second substrate, consider we have an extension on the top and a contraction on the bottom. Okay. So the bending moment will be generated by the gradient stress addressed on the boundary, okay, the cross-section of the beam. So for the MS, finally MS will be equal to MF because it's a steady state condition. So there's no much more force. So the force is balanced. The bending moment is balanced. So these two bending moments need to be the same. So for MS, we need to do the integration, okay, for each individual small force, and each individual small force has a small portion of the contribution to the bending moment here. So each small force will times the arm, the individual arm, and get the final, and then integrate them together to get the final MS. So this will be a integration formula. So we will do that later. So this one is easier. It's the force times the arm. That will give the bending moment of the fin, the force on the fin. So the bending moment on the silicon substrate need to be integrated. Okay. So now we go back to the equation. So now we consider the first one. The bending moment from the fin will be equal to the force on the bending on the fin. So the force will be sigma F times the width and the thickness of the fin. That's the total area, cross-section area, and times the arm. The arm is Ts over 2, roughly. Okay, actually we neglected the fin, the thickness of the fin. So we consider only the substrate, the thickness. Usually the fin thickness is like 1/10, only 0.1 of the total thickness of the substrate. So this kind of neglection is practical. Okay. The second one will be the individual force on the silicon substrate. So individual force will be sigma z. Okay, it's a different stress along the cross section. So this one times z, that's an arm, and also dz. Dz is a small portion of the surface area, and times w, that's the width. So sigma z dz w will be the small force, and then times the arm z. Okay, and the sigma z is a linear relationship along the cross section. Okay, so it's actually sigma z equal to z over dou. Okay, so you have a larger curvature. You have a larger curvature, a smaller curvature, radius of curvature. You have a larger sigma. Okay, so you plug in sigma z equal to z over dou. So you end up got the equation over here. Okay, take a 2 times integration, 1 time integration. You got the final equation over here. So so n out, you equal these two formula, the bending moment together, mf equal to ms. You find out the equation sigma f equal to this kind of relationship. So equation number 4 and equation number 1 now share the same variable. One variable is sigma f, the other variable is dou. Okay, so we can plug in equation 4 into equation 1. Okay, so n out will find out the total formula will become only the function of dou. So the dou can be solved, okay, by using this kind of method. So you plug 4 into 1, and you take some arrangement, you n out, you got the final result. The radius of curvature will become the formula, very complex formula here. Okay, now we need to consider the physical meaning of the formula. So if you want to have a large displacement, that means the radius of curvature need to be small or large. How do you think? Large displacement means a smaller curvature or large curvature. Large curvature, smaller radius of curvature, right? You have a smaller radius curvature. You have a smaller sphere, smaller circle. So that means you have a larger displacement at the end. 就是大的这个比较小的这个曲率半径，给你比较大的变形量。小的曲率半径是很弯曲，所以变形量大。Okay, so we want small though, right? We want small though to get large displacement. Okay, so if we want small though, we want small though. That means we want large bottom, small top, right? Yeah, that's right. Say it again. We want large bottom, small top. In that case, we can get a small though. Small though means a large displacement, large diffraction. Yeah, can you follow it? Okay, so in this case, how to make the though small? Okay, so we need to consider we need to design the material property, the thermal expansion coefficient between the fin and the substrate as large as possible, the difference. Okay? So you have a large beta F and a small beta S, we can have a large, this value here. Currently, we have like 20 something, 22 for silicon, 2.6 for 22 for aluminum, 2.6 for silicon. So the variation is about 20, right, over here. So if you want to enlarge this much more, we need to consider to put the fin, not the metal fin. Maybe we can consider polymer fin. For polymer fin, we can easily get a 200, okay, over here. And this is still 2.6. So we can enlarge 10 times. Okay. Yeah, that's one way. The other way is by considering to increase the temperature differences. But still some limitation. You cannot elevate the temperature too high. Otherwise, the material can be damaged. So these two are the two considerations if you want to increase the displacement. The difference, the first one is the difference of the thermal expansion coefficient. The second one is a temperature differentiation. Okay, now we consider top. We want to reduce the top in order to increase the displacement. So in order to reduce the top, several parameters you can consider. The first one is the TS, okay? The substrate. So if you reduce the substrate, you can reduce the substrate thickness. You can reduce the substrate, reduce the top value easily, okay? That's one way. The other way, you want to make it small. That means you consider the Young's modulus differences over here. If you have you want the top small, so the Young's modulus of the fin, it will be better to be larger than the substrate. This sounds not very easy because it's a contradiction, yeah. Because you have ceramic substrate. Ceramic substrate usually have a very strong Young's modulus. So you want to change into polymer. However, on the other side, you don't have another material to give you strong, thermal coefficient expansion coefficient. So you need to compromise between these two. Try to find some real value plug in and try to find out which one can give you the better though to optimize this one. Okay. So after you got the though, you can plug back into the equation. You can find the moment. Okay. It's too large, so I just using though to replace the whole thing. Okay, over here. So from the bending moment divided by the length, you can gather the force generated by the actuator. That's the final results. So you want to get a large force from the equation. So though is give the equation for displacement, F give the equation for the force. So you want to get large force. Actually, you want to increase the substrate thickness. These are totally contradict to the previous, conclusion. You want to reduce the TS to increase the displacement. Here, you want to increase the substrate thickness to increase the force. So sounds another good idea. So then we look at the bottom. You have a though 1 over though over here. So you have a small though over here, still get a large force. So try to reduce the substrate can give you small though. That can give you a little benefit here, but will also reduce the thickness over here. So another consideration is by using the length. Okay, so you can shorten the length. Okay, to get a larger force. The length is over here. There's another way you can consider in larger substrate stiffness. Okay, so these two equations are the final two equations you need to consider. However, before we plug into the real number, you don't have much physical ideas about how large is the force and what kind of displacement we'll have by using this actuator. So now we consider, oh sorry, I haven't finished yet. So after the force, the displacement will be this equation, the second order derivative will become 1 over though, okay? So you have in 2 times integration, you can find out the final, the total, deflection, the curve of the structure. the maximum displacement will be at the end, x equal to L. So you end up to find out that the maximum one will be L squared over 2 rho, okay? So you want to get a larger displacement, you need to have a longer length, smaller rho. And for smaller rho, you usually will give you large force as well. So, however, the longer distance will give a smaller force here. So you need to consider to compromise between number 6 and number 7. Try to find out the balance, okay? Yeah. Okay, now we plug in the real number. So for example, we use in silicon beam and put the aluminum fin on the top. So as a composite material. And as I mentioned, the thermal expansion coefficient will be 10 times differences, and also the fin thickness will be silicon only 2 micron and aluminum 0.1 micron. That means 100 nanometer. So the temperature elevation will be 100 degrees C. And now we consider we have a beam with a length of 10 micron. It's pretty short actually, and the width is 2 micron as well. So it's a 10 micron beam, 2 micron wide, and 2 micron thick, roughly 2 micron thick. Consider this kind of beam. And we heat it up, okay? So we can find out that the radius curvature will be like a 5 millimeter. It's around like a 5 millimeter. It's pretty small actually. That means that we can have a good, hopefully we can have a good diffraction. So the force from the calculation will be 2.67 micronewton. It sounds not very large actually, okay? And the displacement is also not very large as well. It's a 10 nanometer. Okay? So now you want to consider to enlarge the displacement. I think the easiest way is by increase the length from 10 micron into 100 micron. So from 10 micron into 100 micron, so your diffraction will be changed from 10 nanometer up to like 1 micron, 100 times. Increase the length 10 times, increase the Z 100 times. But at the same time, we'll reduce the force by 10 times. So in order to increase the force, you can consider to increase another parameter, the thickness, the thickness of the substrate. The thickness of the substrate currently is 2 micron. So if we increase the thickness of the substrate here from 2 micron into 3 times, okay, you get a 27 times increment on the force. Originally, you have a 10 times reduction. So now you have like a 2 or 3 times larger force generated here. So if it's 3 times larger force, the force will be close to 10 micronewton. Is falling into the range of our final project. Okay, so you need to do some adjustment on the geometry. Okay, so this only give you a rough idea for the first estimation. Okay, is it easy to understand? Okay, so this for you. If your final project is working on the actuator, so definitely you need to consider those parameters together and try to accommodate them to originate to optimize them. Okay, in a more reasonable way. And also you need to consider fabrication. If you design a very long, extremely long beam to meet a requirement, however, it cannot be fabricated, it's also not practical. So you need to consider different aspects. So at the end, I give you the literature of the thermomagnetic metal flexible actuators, which is similar to the cold-arm, hard-arm actuator. So, so on one side have a thicker beam than the other side. So when you heat it up, it will bend on the sides. Okay, it's bending on the side. So look into here. So one side is thinner than the other side. So when you heat it up, the beam will bend over to one direction. So there's a real fabricated results, and also these are real actuation results. So when you apply different currents, you can see the displacement will be different. So the variation corresponding to the applied current is like a parabolic profile. Yeah, because the input power is equal to I squared times the resistance for total power. So the displacement is actually is a linear relationship to the temperature increment. If you consider the displacement to the temperature increment directly, it's a linear relationship. But if you consider it's into the current, it's become the parabolic profile. Yeah, so this is a kind of actuator we can have. So you can use the equation we developed for calculation. So yeah, so these are simulated results. You can see the displacement of the beam at the end. Okay, so it's usually operated at the lateral driven mode. Okay, some people using this up and down, but you need to consider many layers of application. Not that easy. For the lateral driven, it's a bit easier. Okay, so you can have only 1 or 2 layers of application. You can have the beam structure ready for application. Okay, so now at the end of this kind of the class, so since this is the last class of the semester, so I'd like to give you some guideline for you to prepare the final presentation and also the final report. So the final presentation, the final report won't be easy, actually, okay? So consider we split